Okay. Okay. Welcome. All right. Okay. So. Okay. Woohoo! All right. Excellent. Yay for algorithms. Okay. I lost my little USB thing for this piece, so I'm going to have to be here. Okay. Okay, so is that a tree? What do you think? Is that a tree? Yeah, it's connected. It has no cycles, right? So that's a tree. It's not a shortest path tree like the drawing from before. It's just a tree. Okay. Okay. So minimum spanning tree is what we're going to talk about today. Okay. So let's talk about tree definitions. Okay, so the lecture in a minute is going to be, yeah, I'm sorry, my little thing broke. I dropped it, and it shattered. I'm so sad. Okay, so I usually have a spare, but today I didn't bring it. So these are three definitions of trees: n-1 edges and connected, n-1 edges and no cycles, and all pairs of vertices are connected by a unique path. Okay, I'll argue that. I'll show you that. We're going to talk about a minimum spanning tree algorithm, which is sort the edges and add the edges in this order if there's no cycle, and keep adding edges until you're done, until you get a tree. Okay? The cut property is that it says there exists a minimum spanning tree with a minimum weight edge across a cut, and from that you can prove the correctness of Kriskell's algorithm. Okay? And then there's this union find data structure. The key to Kriskell is it adds edges as long as there's no cycle. Okay? You sort the edges, you pick the smallest one, blah, blah, blah. But if you add an edge and you create a cycle, are you making a tree? No, because the definition, whatever. Okay? Okay. So we have to be able to find that. So these are the union find data structure. I'm going to tell you how to build a data structure that does this. And what we're going to do to prove that you can do it so efficiently is we're going to have these, the unified data structure is a pointer structure. Each element has a pointer to another element, exactly one pointer, right? You've seen pointer structures a lot. You've seen lists and various things. You can point to yourself. What does it mean to point to yourself? It means that you're pointing nowhere, right? You're pointing to yourself. Okay, that's the end of the line for the pointers. Okay, and pointers are really cool because you can just chase them. If you have one pointer outside of a vertex, it's very clear how to get to the next one, right? You just dereference the pointer for that guy. Is that clear? Okay, so it may not be clear, but it should be at the end of the lecture. Okay, and once you have these data structures, this notion of a pointer structure tells you if you just keep chasing pointers, you'll stop somewhere. Okay? And as long as there's no cycles in the pointers. Okay, and union is a way to say you point the pointer that corresponds to X to the pointer that corresponds to Y. You just start putting them together. You're sticking these pointer structures together. And union by rank tells you can do this so that the depth, the amount of chasing, the pointer chasing you're doing is at most O of log n. Okay? And the idea is to point to a larger rank root. Now, of course, this begs a question as to what is rank. And rank is something, but basically you increase the rank of the pointer structure when there's a tie. That's the basic idea. Okay, so that's the lecture in a minute, and that gives you that you can prove that any rank k root tree has a lot of nodes in it, which shows you that the depth of the structure is small. Okay. Oh no, did I do this again? Okay. Sorry. When I work on the slides, I worked on part of them. So, okay. I don't have the MST part in there. Okay. Okay, so, yeah. Okay, you got all that. So trees, a tree is a connected graph with no cycles. And the property of a tree is it has exactly n minus 1 edges, where n is the number of vertices. Okay? And why is that true? Okay, you start with an empty graph with n components, right? Okay. Sorry. The animations don't work if you don't compile it twice. Okay, well that didn't compile it twice. Okay. Jobs. Kill. %3, %2, %1. Okay, PDF, LaTeX. Okay. Oh yeah, that's a tree. That's a lecture in a minute. Okay. So that's the empty graph. And now adding any edge between two components. How many components are there now? Yeah, they're all by themselves, right? So, right? So we're adding edges between components. We're adding edges between two components. Can we add this edge? Should we add this edge? No. That was not the best edge to use. But we shouldn't add another edge between the two same vertices. But it would have been better if I said we shouldn't add an edge between A and D, because that creates a cycle. Okay? So you always have to add edges between components in this argument. Okay? And every time you add edges between components, you reduce the number of components by 1. Right? So you started out with 5. Right? And then now how many do you have? 4. Now you have 3, right? A, B, D, C, and E. And now you have 2. Now you can't do that one. Now how many do you have? 1 component. Now, can I add any more edges? If I add any more edges, I'm going to create a cycle, right? Because I'm going to be adding an edge in the same component. Okay? So I can't add this edge, for example, right? If I add A to C, you see the cycle there? So the whole number of edges I added in this process, I started at n components, and what do I get to? In the end, it's got to be connected. So how many connected components are there? 1. So how many times can you add an edge? N minus 1, right? That's where the n minus 1 comes from. You go from n to 1, okay? So that's the proof that any tree has exactly n minus 1 edges, okay? Okay. Okay, so a tree is a connected graph with no cycles. Okay, so this is the definition. And a connected graph with n minus 1 edges is a tree. Okay, this is a different definition, right? Do you see the difference between the definition? The property says, the second property doesn't mention cycles, right? But it does mention n minus 1 edges. Is that clear? Okay, so now we want to say these properties are equivalent. These definitions are equivalent. Okay? If not, there's an n minus 1 edge connected graph with a cycle, right? Because this is connected, and it has n minus 1 edges, and if it doesn't have a cycle, it's a tree. Okay? Already. So we know that if not, there's an n minus 1 edge connected graph with a cycle. Okay? But like here's an n minus 1 edge with a cycle. Now what we do is we remove an edge on the cycle. Okay, if we remove an edge on the cycle, does it stay connected? Does the graph stay connected if we remove an edge on the cycle? Yes. Okay? Okay, so now how many edges does it have? N minus 2. It used to have n minus 1. Now it has n minus 2. I mean, that's a lie because this picture, it's not true. But right? It used to have n minus 1 edges, and it has a cycle. Now if I remove an edge, it has n minus 2 edges. If it has n minus 2 edges, can it be connected? No. Right? It must have n minus 1 edges to be connected. That's what we just argued before. And so you have n minus 1 edges. This graph has n minus 2 edges, and you must have at least n minus 1 edges to be connected. This is like something Bart Simpson says, or Homer says. Homer says. Okay, sorry. But it's a fancy term for it's a contradiction, right? Right? So there's no cycle, right? Does that make sense? That's what Homer said when he's saying contradiction. There's something, and the problem here is every step in the argument is fine, except if not. So we assume for the sake of contradiction, there is an n-1 edge connected graph with a cycle. Now we've contradicted that, so therefore any connected graph with n-1 edges, it does not have a cycle, and it meets the definition of the tree. Okay? Okay, so now another definition is a graph is a tree if and only if it has a unique path between every pair of nodes. Okay? So let's prove that. If there's two paths, it looks something like this. You have some pair of nodes where there's two paths that are different, right? You have to have at least two paths that are different. And this is sort of fairly general. Okay? So now somewhere along this path, the path forks in the woods. You know this Robert Frost thing? The two paths diverge in the woods, right? You see the node here where the two paths, if they're two different paths, they have to differ starting at a node somewhere along the paths. Okay, so they differ. And then, moreover, they have to come back together because they end up at the same place. Okay, so there's a node where they diverge, and there's a vertex where they come back together. Okay, now do you see that little thing in the middle? What is that? It's a cycle. So is this a tree? No. You're a good man. Or a person. Sorry. Okay. So. Okay. If yes, it's connected. On the other hand, if there's a unique path between any two nodes, it's connected, right? And it has no cycle, right? Because it's a unique path, there's no cycle there, right? So, okay. Okay, so because a cycle itself creates two different paths between two nodes. Okay, so the second part is easy. Okay. Okay, so now let's talk about minimum spanning tree. Okay, so this is you're given a graph and edge weights, WV, and you want to find the cheapest possible connected subgraph. Maybe you want to think of these edge weights as cost. Okay. Okay, so now. If you want to find the cheapest possible connected subgraph, is that going to be a tree? Will it be a tree? Well, it depends on it depends a little bit. What if I have the weights be negative? Yeah, nasty. Okay. Okay. If edge weights are positive, it will be a spanning tree, because then why add more edges, right? Because each one adds cost. Okay, so if negative edges, then you can have negative weights, but then we define it as being a tree. Okay? The problem can be defined with negative weights, but when we say the minimum spanning tree problem, we mean you want to output the tree of minimum sum of total weight. Okay? So it's just a definitional thing. So, okay. So now find the lowest weight spanning tree. And now the way we define this, what we really wanted in some sense is the first thing. That's the intuitive thing. But the way this is defined is this way. Find the lowest weight spanning tree. So the thing you have to output must be a tree. Okay? And you want to find the one that minimizes the sum of the edge weights. Okay. Okay, so that's the graph. Is that a minimum spanning tree? Now, is it a shortest path tree from S? Yes. Okay, so I'm just pointing out that they're not the same thing, right? Shortest path trees and minimum spanning trees, they're not the same thing, okay? Okay. How about this one? Is that the minimum spanning tree? Just to make sure. Right, because it seems like there's only really three possibilities, right? You delete any one of the edges in the cycle, and you can see that this one results in the cheapest cost. Okay, so this is one you can check by enumeration. You don't have to be clever; you just try everything. Okay, and it's not the shortest path tree from the node S. And you can construct examples where the minimum spanning tree is not the shortest path tree from anywhere. Okay, so they're really different objects. Okay? Okay, so this is the cheapest spanning tree. You're trying to, in some sense, what is an example is you have a place where it's called the muddy city problem. There you want to connect up all your cities, and you want to pave a subset of the roads as cheaply as possible, so when the monsoons come, you can still drive on paved roads, right? Okay, that's the minimum spanning tree problem. In the worst case, there's access from anywhere to anywhere. It's really, it's a network design problem where you're trying to build a network of cheapest cost that ensures everybody's connected. Okay? Okay, so you don't care about the shortest path here. This is like a disaster relief sort of situation. You just want to make sure everybody can get anywhere. Okay? And you have minimum cost. So let's try this. So what's the minimum spanning tree? Oh, I have no idea, but I think the animation will show us. Okay, but I have an idea what to do, right? Because I know the algorithm. But it's also clear what to do. In some sense, like maybe we deceived you before, right? We told you all these clever algorithms. In fact, there's really things that aren't clever at all. And this is what this chapter, well, it's sort of what this chapter is about. It's called greedy. And greedy is like do the obvious thing. So what's the obvious thing? Which edge would you like to add? Yeah, C to E is the edge, but yeah, the one of weight 1, right? So, okay, I'm picky about terminology. Okay, so that's fine. We can add that. What edge do we add next? A to D. Okay, good. And what's that? Now you get a choice. Which edge do you want to add? I have no idea what I did. Okay, there you go. That's what I did. Okay. So now what should I add next? B to E, right? Yeah, no, that's a mistake, right? Because it creates a cycle. Okay, I don't need it. I've already connected B to E. I don't need to add this edge to connect B and E, or to connect any of the nodes B, C, or E, right? So I don't do that. Okay, and then I add this, and then there's one more. Yeah, I try to add the ones that I checked 5, and what I do here you can visually see that there's a cycle. But when you're writing code, there's no visually seeing anything, right? You have to figure out whether that creates a cycle. Does that make sense? There's an algorithmic problem here that we're going to use a data structure to address. Okay? So, and here too, I can see that C and D are in the same, let's call them components, right? You remember connected components. We talked about them. So if the edge goes between 2 nodes in the same component, it creates a cycle. Okay? And finally, you do that. Okay? So the total cost is, I guess I'm adding up the numbers. Okay? Is that clear? Okay, so that's sort of the algorithm. Already said it, right? What we did is something fairly greedy. We sorted all the edges, and then we just started adding them in order, unless we didn't need them. Okay? Unless we created a cycle. Okay? Fairly simple algorithm. So, why does it work? Okay, so we're going to talk about this property of minimum spanning trees. And let's say you have a cut. Now, that's a partition of the vertices into two pieces. Okay? That's what we mean by a cut in this slide, or in this chapter. It's not a vertex cut. It's just a partition of the vertices into two pieces. All the vertices in S, and all the other vertices in V minus S. Okay? Now you take all the edges that go across this cut, meaning it has one endpoint on one side and one endpoint on the other side. Okay? So now you take the minimum weight edge across this cut, the smallest weight edge. Okay? And now we're going to say the smallest weight edge is in some minimum spanning tree. Okay? That's what we're going to argue. That's the property we want to argue. Okay? So the tree is connected, so there's some way to get across this cut, right? Look at these 2 endpoints. Say we already have a tree. We have a minimum spanning tree, and it doesn't include this edge. Okay, that's what I should have said first. Okay, there is a minimum spanning tree that doesn't include this edge, just for the sake of, the proof. Okay? There's definitely some minimum spanning tree. If it includes the edge, we're done. If it doesn't include the edge, we know it's connected. Right? That's what a tree is, a spanning tree is. So since it's connected, we know the endpoints of E are connected. So it means there's a path from the endpoint in S over to the endpoint in V minus S. Right? So that's what I'm drawing here. And at some point, that path crosses between these two, this partition. Okay? Crosses from S to V minus S. Let's call that edge E prime. Okay? So now, what I can do is there exists an edge E prime across this cut because we know the spanning tree we presume exists, and it doesn't contain E. So there's some edge that goes from S to S, V minus S. Okay? Is that clear? Okay, so now what we do is we're going to just replace E prime with E. This is fairly straightforward. Okay? Okay. So now we're going to replace it. Now we're going to say, what do we have to prove to say this is still a spanning tree? Okay? So we have to prove it's connected. So every pair of nodes has a path between them. Okay? So we know that every pair of nodes used to have a path between them. And before you changed this graph, right, you've changed it. You've removed one edge and you've added another. So maybe they're not connected anymore. But there's two cases. First, the pair might be on the same side. It might not use this edge E prime. If it doesn't use the edge E prime, all the other edges are still there. Okay? So now, but then there's the other case where the old path between this vertex U and this vertex V used E prime. But now you can connect them by using this path up to E and then back down to the endpoints of E prime. Okay? So now you can say that you know that everything that was connected before is still connected. And everything was connected before, so everything is connected. All the pairs are connected. Okay, this is the cut property. Okay? And the number of edges in this tree is n minus 1. Right? Because we deleted an edge and we added an edge. So now we have a graph that's connected, and it has n minus 1 edges. So therefore it's a tree. That's the property we proved at the beginning. Okay? So still a tree. Okay, now finally we know that the cost of this tree is no more than the cost of the original tree. The original tree was a minimum spanning tree, and now this new tree is no more costly than the old one because the weight of E, the weight of E, is less than or equal to the weight of E prime by the definition of E. E is a minimum weight edge across this cut. Okay? Okay, so it's still not only a tree, not only a spanning tree, it's also a minimum spanning tree. Okay. Okay, so now this is the algorithm. Okay, for F equals the empty set is what it should have said. For each edge E, if there's no cycle, what you do is you add the edge to this forest. Okay? So the key here in this algorithm, in this implementation, is how do you check for a cycle? You know how to sort the edges. You've done sorting, right? N log n. Okay, so how do you check for the cycle for the edge U, V, and F? Okay? Okay, so now that's not too hard, right? Because you can check for a path between U and V in the forest. Right? So you know how to do that. You can do depth first search, you can do breadth first search, and you can see if they're in the same connected component. Right? But that takes time, right? It takes order n time. Why does it not take order m time? Why does it only take order n time? Why doesn't it take the number of edges time? N is the number of vertices. Why does it not take the number of edges? Well, how many edges are in F at most? How many edges are in a tree? N minus 1. Right? So you know that F, the size of F is only order n. It's smaller than n minus 1. So it's order n. So you can run in this graph that consists of the edges that just correspond to F. Okay, and there's only a linear number of edges there. Only n number of edges. So this is order n times m for Kruskal. Okay, which is fine. It's something, but now the question is, can you do better? Okay? So now the key here is the main issue here in this algorithm in terms of implementation is to check for the cycle. Okay? So one thing we want to do is, as you notice from the beginning, in the very first slide, I talked about in the spanning tree, we're like, what you're doing is you're adding edges and you're creating connected components. So you really just want to understand the connected components. Okay? Now the connected components are disjoint, right? This connected component and this connected component are different. If they had an edge, a vertex in common, then they would be the same connected component, right? A connected component is a maximal set of connected nodes. Okay? So we want to sort of maintain this notion of who's in which connected component. If we could write down the connected component number for each node at all times, all we'd have to do for an edge is check whether they have the same number, right? And then we know that they're in the same connected component. So then we would know not to add the edge. Okay? So now what happens in this algorithm, at the beginning, each node is by itself. Everybody's in a separate connected component. We saw that in the very first figure and several times. Okay? Adding an edge joins two components. Right? So now you want to check whether UV is in a cycle. What you're asking is whether U and V are in the same connected component. Okay, so this is the data structure that's allowing us to implement this. Much like we did for Dijkstra, we talked about the data structure, which was this priority queue. This is a different data structure for this problem. Okay, and it's allowing us to maintain these connected components as they get merged. Okay, so the first thing is you just make set, which makes a singleton. Every node you're going to do make set. You're going to make a connected component by itself. Okay, and then find. What it's going to do is it's going to find the name of the set that contains X. Okay? And then finally what you're going to do is when you put an edge between two connected components, you want to take these two sets, which are two different connected components, and join them into one set. So you want to union the sets. Okay? So this is what you need to do. And now what do you need to do when you want to if-no cycle? See, this is how you tech. The if-no cycle, the blue line there in the procedure, is just saying, calling this data structure, saying, are they in the same connected component? Okay? This says they're not. It's not going to make a cycle. Okay? If they're in the same connected component, these would report the same name. Right? Okay. Okay. So, okay. An add edge, what does add edge correspond to in this data structure? What do you do there? That's the other thing. The second thing. You union the two connected components. Right? You union the connected component that corresponds to U and the union the connected component that corresponds to V. You put them together into one connected component. Okay, so this data structure will allow you to implement crystals. Okay? Algorithm. Okay, so here's how you do it. I mean, in some sense, people may have implemented this in 61B. Okay, good. That's fine. So we're going to prove some things about it today, and we'll prove some more things about it on Wednesday. The things we prove on Wednesday will be frightening. It's frightening. So let's not go there yet. Okay, so today it's going to be fairly gentle. But do keep it in mind. That it's going to be frightening to live up to our reputation as algorithms, as Berkeley. So, okay, make set. Okay, we're having a pointer structure. Okay, each node has a pointer, one pointer, and it's going to be pi of x. Okay, now pi of x originally is just going to point to itself, so it looks like that, right? Pi of x points to itself. Now find is what it's going to do is it's just going to chase the pointers until it finds somebody who points to themselves. I should have had R point to itself in the figure. Okay, that's all it's doing. It's just recursively find of X is going to say, oh, my parent is not me, so I will then find of Z and so on. That's what the procedure is doing. Okay? At R, it'll say R's parent is R, and it'll stop and return R. Okay? Now, the key for this thing, for X and Z, what will they both return? Yeah, for anything along this path, what will they return? They'll return R. Okay, so it's two people sort of in the same pointer structure will return the same name. Okay? Right? So that's what you want to find to do. For things that are the same in some way, you want them to return the same name. Okay? We don't care what the name is as long as it's the same. Okay? Okay, so how long does find take? Yeah, I don't know. It depends, right? It depends, right? You want the depth to be small. It's the depth of this pointer structure, right? Whatever that is. Okay, so it could be very deep. It could be, we don't know how these pointers are made, so it could be very deep. Or it could be very shallow, right? In some sense, that one is very shallow. So it all depends on the depth, right? The depth of this pointer structure. Okay? So here's the algorithm. So, did I do union? Oh, yeah. Union. Oh, I should have done union. Union. Okay, what does union do? Sorry, I didn't go over union. But union, what it does is it takes the root of one of these pointer structures and points it to the other one. That's all it does. Okay, so now if X and Y used to have two different parents, one of their parents, one of their roots points to the other one. So after this operation, find of X and find of Y will both point to the same root. Okay? Does that make sense? So after you union these things, I take the roots pointer, they both have roots. Find of X returns a root. Find of Y returns a root. Now you point one root to the other. So now find of X or find of Y will return the same name. Okay. Okay. So now we're going to... Now, it could be that if you do unions in the wrong way, you can make a deep, deep data structure. But we're going to try to do it so that we're trying to make it so that the actual depth is fairly small. Okay? Okay. So union. Okay, which points to which, right? We weren't very specific. We just picked one to point to the other. Find that we had the root of X point to the root of Y. We just didn't care that much, right? Okay. So intuitively, what you want to do is, look at the nodes in X. If there's fewer vertices in X and there's more vertices under Y, you're making the vertices in X suffer because now they have to chase an extra pointer, right? So you should really put the point to the one with the more vertices to make a fewer number of vertices suffer. Right? Once you point a root of one to the other, all the vertices in here, any find in them, needs to go through this extra link. All these do not. They did not change. Okay? So you should point sort of toward the bigger one. You shouldn't disturb the root with more vertices underneath it already. Okay? Okay, so now we're going to do union by rank, which is we're going to find the root of X and the root of Y in this pointer structure. Now, if the rank of R of X is less than the rank of R of Y, we're just defining this rank. Initially, they're all 0. We sort of think of rank as size. So who should point to who? If you think of rank as something that corresponds to size, bigger rank is bigger size, who should point to who in the next instruction? Yes. Okay. Yes, I got it right. Okay, so, and otherwise, you point Y to X, right? Okay, but now this is stupid, because does the rank ever change? I never updated the rank, right? So this is all rank zeros and makes nothing, it does nothing, right? So we just change the ranks at some point, right? Is that clear? Okay. If the ranks are tied, then you raise the rank of the root by 1. Okay? So, because this one, if the ranks are tied, what I'm saying is, somebody pointed to me, I got bigger, they were about the same size as me, let me promote myself by 1. Right? It's like a bureaucratic organizations, right? You just keep going up, right? So, does that make sense? Okay, if somebody starts reporting to me and they were at the equal level, my level goes up. If somebody starts reporting to me and they're at a lower level, who cares? Right? Okay. That's the idea. Okay, so does that make sense, this tie thing? Okay. Okay, Pop's got a higher rank. So Dad's got a higher rank, or Mom, if you prefer. I mean, this is a weird thing because you only have one parent, so whatever you want to call them. They. Okay, so again. Okay, you got a higher rank, okay? It's more amoeba-like anyway. But, so rank of X is less than or equal to rank of pi of X, right? Always. Does that make sense? It's not less than or equal to, it's bigger. Somebody who you point to is bigger, right? Okay. And why is that? So that's what the code enforces. It says, if my rank is less than, strictly less than the rank of Y, that's the time when I get to point to it. Okay, so that meets the condition. You have to see when I set the pointer, is this true? Okay, because then ranks only go up, right? And the ranks inside don't ever go up. Once I point to somebody, I always point to somebody, my rank never goes up. Okay? So here it's true, this condition is true, rank of X is less than rank of Y by the enforcement. And here now we set the parent of Y to X, and we increase the rank of X if there's a tie. Okay? So now you have this sort of total order. Up the pointer chasing. Okay. Initially it's true because you have no parents. Okay, so that's what this extra condition is. It's not. You have to. It's not actually true. You have to add this blue condition here, which I just did. Right. Right. You have to say initially. You have to do the base case. That's all. Because pi of X is yourself at the beginning. Your rank can't be higher than your own. Okay, so this is what it says. Any rank K root node has a lot of nodes. Okay, if my rank is K, the number of descendants I have is 2 to the K. The number of people whose pointer structure, if I chase them, end up at me is 2 to the K. Okay? It's very large. Okay? So it's exponential in my rank, the number of vertices below this root. Okay, so it's induction. So what's the base case? What's the base case? Is it A or B? Just to get you oriented. What's the base case for the induction? Yeah, because initially everybody has rank 0, right? That was initially. Okay, and they have one node in them. Okay, one vertex. Okay? Now the induction step, when rank of X goes up to K, okay, just take 10 seconds and try to prove it to yourself. It's that line there, right? It's in blue. Was that 10 seconds? I don't know. Do you see why? Rank of X goes up to K. Okay. When it goes up to K, this thing fired off. Somebody's rank got raised. Right? So what was each one of those guys' ranks? K minus 1. How many vertices did they have in their tree? Yeah, somebody emulate him. Yeah, 2 to the K minus 1, right, each. And now together, how many do they have? 2 times 2 to the K minus 1, and you're done. Right? Okay, so let's see that. Rank of X was K minus 1. So it has greater than 2 to the K minus 1 nodes by the inductive hypothesis. And it gains nodes from another rank K minus 1 node, which has greater than 2 to the K minus 1. This is equal to 2 to the K. Okay? So that's the proof. Okay? It's set up very cleanly, this whole thing, unlike what will happen later. But, okay. So did I just prove there's exactly 2 to the K nodes in a tree of rank K? Is that what I proved? No, not quite. All right? What could happen is, I could gain children from people who are little. They weren't even worth bothering. That's exactly what I said before. If I get more direct reports who are lower than me, I don't even care about them, right? Whatever. I didn't get a promotion. So, right? But I got more people, right? Okay, so that's what I'm saying. Gains nodes without gaining rank. Okay, so I just want to, not that it's important. It's not important that this doesn't happen, but I just want to, you should always understand what you're proving and not what you're not proving. Okay, now find x is which one of these? How long does it take to find the root? Remember, it's the depth of these trees, right? And we proved two things. Any rank k node has at least 2 to the k vertices below it in its tree. And we also proved that every parent has a higher rank than their child. Okay? So every time we go up, every time we do a find, when we chase a pointer, we find a higher ranked guy. So if you start at 0, we chase one pointer, we go to 1. If we chase R pointers, we go to rank R. And how many nodes does that have? 2 to the R, at least. Okay? So now, once you have that exponential thing, right, it's 2 to the depth, the number of nodes in this tree. So now answer the question, which one is it? Log n, right? Because the depth is the cost. The depth is the cost, and it's 2 to the depth is the number of nodes in a tree, and there's no more than n nodes, right? Okay, so now let me just do, I just like to repeat before I show you, after I show you, and after I show you again. Okay, so, A and C, right? It's also C because this is a trick question, right? Right, it's also O of n, right? But, so rank of k root nodes has greater than 2 to the k nodes. Only n nodes in any set, so every rank is at most log n. Otherwise, there's more than 2 to the log n nodes in a tree. There's only n nodes ever, n vertices ever. And the parent has a higher rank. So the code enforces it, right? We showed that every parent has higher rank. So there's only k steps in a find, which is order k, with the maximum rank of any vertex. And the maximum rank is O of log n. Okay? And that's great. And now the question is, can you do better with this union find data structure? And you can. And how did you do, quote, better in 61B? What was the other heuristic you used? Path compression. Okay, so you can do better if we do path compression. And we'll talk about that on Wednesday. And unlike in 61B, I guess, 61B, we'll prove you do better, but it won't be pretty. Actually, it's beautiful, but not pretty, right? Just beautiful. It's stunning, actually. But okay, but we'll do that. We'll see better. Okay? So now the Crisco's implementation was you have V finds and V unions and E finds. So it's O of E log n time, which is way better than order V times E. So versus this thing. And lecture in the minute is what should you understand? You should understand how to work with trees. You should be able to make these kinds of arguments that we did, and you can see them again. Crisco is, this whole idea is this is greedy. And we're starting with the greedy chapter. So the greedy chapter this is where it says do the obvious thing. So just be a little careful here, right? Because when I say do the obvious thing, it's not always obvious what the obvious thing is. But afterwards, you're like, oh, that's obvious. Okay? So here the thing is we did the obvious thing and we put the edges in order, but we had to be careful not to add cycles. So even in here, there was a subtlety. And even in here, we really had to prove that this was okay. And the cut property was crucial in proving that this obvious thing worked. And you have to be able to do it. And in particular, what we did is we said, look, there might be another solution, but we can change that solution by switching an edge into this solution. So we didn't make a bad decision. Okay? This is called the exchange property of greedy algorithms. Okay? And now the union find data structure. Here, the idea here is really a classic computer science idea, right? You want to keep the depth small. So what you do is you sort of break ties by pointing to the bigger guy, okay? And that sort of always gives you this logarithmic behavior. So that's also a sort of a paradigm we see a lot. Okay? And union by rank is how we did that. All right. Okay, thank you. I don't know. What do you do? What did the code say to do? You looking for the thing that flew out? Yeah.
How big was it?
It was a USB plug-in.
Oh, okay.
Yeah, so it's about this big.
I know.
Yeah, it's just that thing with a wireless thing. Yeah, what did the code say? Here. Okay.
There is something in there.
In there. Oh, I see it. You're right. Yeah, I got it. Okay, so there must be a pointer. Maybe a stick, yeah. Do I see a pointer here? You see it? Yeah. Yeah. Well, you point to the bigger rank, but you add one if the ranks are tied. Right? Does that make sense? Yeah, okay. Okay. I got very long arms. Well, assuming my arm can get in there. Okay, well, I shouldn't have been working out. It's a little bigger than it used to be, my arm. Almost. Okay.
There
Here.
might be another one there, but...
No, that's bolted to the floor.
Okay, let me
try one. Okay.
do it.
No, I did not. Let's see what I should do. Here, I'm going to go fishing. Here, I'm going to go fishing. You want me to try this?
From behind. Oh.
Okay. I think I got it closer. It landed on that. That's so funny. That's exactly what I did before.
Yeah?
At least I think I...
You and I have lots of things in common.
Well, I hope it